Hello, everyone, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Allison Schick. Allison joined Thermal Analytics as a thermal and CFD engineer in 2019, shortly after receiving her bachelor's degree in mechanical engineering from Binghamton University in New York. She helps our customers utilize various TAI software packages and extensions by providing support throughout projects, responding to technical questions, and leading training sessions on TAITherm, cotherm, and human thermal modeling. She specializes in modeling cabin environments to evaluate human occupant thermal comfort, as well as automating workflows for coupled simulations or for efficient pre-post processing. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar, and we'll send you the recording link when it becomes available. And with that, Allison, if you're ready, you may begin.
All right, thank you, Chris. This presentation is going to cover some of the best practices to keep in mind when you set up cabin simulations in TAITherm. Cabin simulations can be complex, and we know it can be beneficial to have guidance on how to pick the right geometry, right boundary conditions, and solver settings to get the best, most trustworthy results. We're going to start with the model setup best practices. The first step for any simulation is choosing the geometry to use and meshing that geometry effectively for the simulation. Once we have the geometry chosen, we'll move on to some recommendations for cabin model inputs and human model inputs. Convection is typically important for cabins, so we will also highlight the options for internal airflow as well as external airflow. And then we'll discuss preconditioning of the cabin and the human. Once we've gone through the model input recommendations, we'll have some tips on how to efficiently run the models while avoiding model divergence, and then we'll go through the post-processing options that can make model analysis simpler. And I'll also show a couple examples of how we can identify model setup errors by looking at the results. Before we jump into that content, I want to make sure that we're all familiar with the software tools that I'm going to mention throughout the presentation. TAITherm is our advanced 3D thermal simulation software to evaluate real-world performance. It allows for 3D thermal simulations of either transient or steady-state scenarios, and it'll account for all modes of heat transfer: conduction, convection, part-to-part radiation, as well as solar radiation. RapidFlow is our new 3D flow solver specifically designed for convective heat transfer analysis and airflow applications. It allows you to obtain high-fidelity fluid results while maintaining efficiency of model setup and model run times. And lastly, we'll be talking about the human thermal extension, which is an advanced technology for evaluating how humans experience and react to a thermal environment. It has a bioheat model that automatically does thermal regulation as the simulation runs, and it will provide physiology results as well as comfort and strain indices. All right, we're going to start with some advice on cabin model setup. The first place we typically want to start with model setup is choosing the geometry that we're going to use. For this type of simulation, we're going to need some geometry representation of our vehicle and of our human. So we're going to start by looking at the vehicle geometry. You may choose to model the cabin interior and the full vehicle hull, or you might just choose to model the cabin only as shown on the right-hand side of the screen. The level of detail desired and the purpose of the simulation is going to help you to decide what's best. Here's a handy flowchart to determine if we can just use the cabin interior geometry or if we should include the full vehicle hull. If the purpose of the simulation is to get both internal and external temperatures, maybe for validation purposes, in that case, we should keep the external geometry. If we want to model underhood, underbody components as part of the simulation, it's also important to keep the surrounding parts, so we should keep all of the external geometry. And if we want really accurate external flow, whether that be from RapidFlow, CFD, or library convection, in that case, we would also want to keep the full vehicle geometry. If none of these seem to apply to your scenario, you could choose to only keep the cabin interior surfaces. An example of this case might be something like a completely still vehicle, so there's not very significant external airflow, and the cabin is a heat up in a cold environment, so there's no solar loading. The less geometry you use, the less calculations the solver has to perform. So the model will be able to run faster if we exclude the vehicle hull. But if you don't care about runtimes and you already have the full vehicle meshed, you can also always choose to keep all of the external vehicle components. Sometimes they're nice to have if you plan to make nice visuals or animations of the results. So using just the cabin interior surfaces can be accurate depending on the scenario, but still sometimes people choose to keep the full vehicle just for visual purposes. In selecting your human geometry, there are a few things we want to consider. First, the human should be positioned reasonably to interact with the cabin. If they are driving the car, maybe we have both of their hands on the steering wheel and we place their foot near the gas or brake pedal. If the person is a passenger, their arm should be relaxed by their side or maybe resting on an armrest. The positioning of their feet and hands can significantly affect the human thermal results. You might picture a time when you were in your car on a winter day and the HVAC vents were pointed directly at your hands on the steering wheel. In that scenario, your hands are going to heat up a lot faster than if you had the vents pointed away from your hands. Also, when placing your human geometry inside the cabin, try to make sure that you have the human not penetrating any other parts. Instead of having them intersect with the seat, try to have them hover a few millimeters away from the seat surface. The error from those kind of intersections might be minimal when we connect the human to the seat via thermal links, but it's a best practice to not ever have penetrating mesh because the penetrating mesh leads to invalid view factors. For example, if your human's back is intersecting through the seat back, there's going to be a view factor from the back of the human to the interior of the seat, which obviously is not the situation in real life. An automotive seat will compress when you sit on it, so the best way to avoid penetrations is to actually morph the seat cushion and back around the human body. When choosing your human geometry, also be careful to keep somewhat close to the real physical size of the person that you want to model. TAITherm will scale the human segment sizes behind the scenes to match up with whatever human percentile you choose. But if the human sizes are dramatically off from reality, the human won't be interacting with the other geometry in the model correctly. For example, if you have the human hand way smaller than it would be in real life, it's not maybe going to be in contact with an appropriate amount of the steering wheel. Also, if you're modeling airflow with RapidFlow or CFD, the person's size and positioning is going to affect the airflow patterns in the cabin. So it's good to be kind of close to reality when deciding the size of your model so that the results are as accurate as possible. The human model in TAITherm is a multi-layer shell mesh representation of human body physiology. Each part of the human that you see in TAITherm is actually 16 layers of bone, organs, skin, and other viscera and whatnot. These layers are all being used for the calculations. So for every element, a calculation has to be done at each of those 16 layers. And because of that, the mesh count for the human can have a really dramatic effect on the model runtimes. If you make the human mesh extremely small, it's going to have a performance penalty. We recommend a mesh size of about 5 millimeters to 20 millimeters. You might want the mesh to be smaller on small components like the fingers or toes, and then you can make it a bit larger on large areas like the torso or legs, like we see in this example geometry on the slide. When modeling humans in our cabins, we also have to think about their poses. The easiest way to pose your human is during your mesh prep in your meshing pre-processing tool. When you're posing the geometry, make sure you are bending or rotating the parts at appropriate points like the elbows, knees, or other human joints. This will just make sure that the person is in like a physically possible, comfortable position. If you don't have access to a meshing preprocessor, we do have a few different cabin-related poses that we can provide to you. The options like a one-handed driving grip and the passenger pose with the hands at their side are shown here. All of these are available and we can send you the mesh for these specific human poses if you request them via the support site. Just a few other notes on meshing before we move on to the boundary condition setup. You should always be sticking to the standard thermal mesh quality criteria. Your meshing software likely allows you to do mesh quality checks, and we recommend you keep the quality within the limits listed here. If the mesh is really low quality, it might diverge when you try to run the model, or it might just take many, many iterations to get to convergence. So trying to save time by doing low quality meshing at the start might actually cost you more time later trying to figure out why the model keeps diverging. Along with that general quality criteria, you also want to be checking for penetrations. When you import the human into the vehicle geometry, make sure that their head isn't popping out of the roof and their feet aren't intersecting with the floor. It's also a good idea to check the normals orientation for both the human parts as well as the cabin parts. Orienting all of the cabin parts in the same direction is going to be really helpful for efficient model setup. If the windshield has like the back facing the environment, but the floor has the back facing the vehicle interior, the model setup can get kind of confusing. The human must have the front side facing out because the back side of those parts is assumed to be the internal body. So it's really easiest to just have all of the front faces for the cabin parts and the human parts oriented into the cabin. Once we've done all of our geometry prep, we're ready to actually set up the model. A mistake that we often see people make when setting up their cabin is not having an appropriate thermal resistance through the vehicle walls, roof, floor, or doors. Too low resistance will cause too much of the heating or cooling energy from the HVAC system to leave the cabin, and too much resistance will cause not enough energy to pass through to the environment. To calculate resistance, you can use the equations on the slide. R is the resistance, L is the thickness through the layer, and K is the thermal conductivity of the material. Oftentimes, people use multi-layer parts to model the various layers of the walls and doors, and you can just sum up the resistances of all of those layers to get the full thermal resistance through the part. If you're running a heat up simulation and it seems like the air temperature in the cabin is not getting warm in the expected amount of time, this is when you might want to double check these resistance stackups. Sometimes when using multi-layer parts, people maybe forget to include an air gap, or they maybe had to make assumptions for the vehicle exterior material properties, and they just underestimate what that full thermal resistance is going to be. Oops. Checking the resistance is going to be the simplest way to make sure that the material properties for the cabin are realistic. And here on this slide, we have listed some ranges that we commonly see for reference. Here's an example of calculating that material stack up for the specific door. Let's say for this case, we want to evaluate HVAC performance, but the material supplier for the cabin only gave us the thermal conductivity and not the thicknesses of any of these parts. We could guess the thicknesses using our engineering judgment, but we should check to make sure that those guesses are somewhat close to reality. So here I would put in the thermal conductivity provided by my supplier, and then I put in the estimates for each material thickness through the full stack up of the door. We can then calculate the material resistance for each of those layers, and then we can sum all of those up to get the full stack up resistance. On the last slide, we saw that a door resistance is usually somewhere in the range of like 3 to 8. So if we had estimated these material properties, this would help us to know that we're kind of on the low end, but it's likely realistic enough. If the resistance of this full stack up was something like 0.5, that is likely way too low and we should go increase the thicknesses or else our cabin is going to be losing too much energy to the environment and it's going to affect the accuracy of the results. Another important aspect of cabin modeling is the glass properties. Though there are some default automotive glass properties available in TAITherm, it is recommended that you supply your own custom glass material properties. The properties for automotive glass can vary greatly based on the supplier and the vehicle. And if there's any solar included in the model, those glass properties are going to have a big effect on the cabin internal surface temperatures and the human comfort. To set up your own custom glass properties in TAITherm, you need to know the transmittance and reflectance. The transmittance, reflectance, and absorption are always going to sum up to 1, so you only need to know 2 of those 3 inputs. You also need to know the thickness. The glass material properties are always measured at a specific thickness, and if the thickness in the model varies from the sample that was measured, the material properties are going to change. Moving on to some human setup, you likely want to have your human have conduction between themselves and some of the cabin geometry like the seat back and the seat cushion or the steering wheel. To allow for those conduction pathways, we recommend that you use thermal links. If you're unfamiliar with the concept of TAITherm thermal links, it allows you to create conduction pathways between disconnected mesh, and it removes convection and radiation from the calculation when 2 parts should be modeled as pressed up against one another. To make a thermal link, select the 2 parts you want to connect. Make sure that you are connecting the proper faces. We don't want to connect the internal organs of the human to the seat back. You want to make sure that you're connecting that clothing surface to the seat back. Next, we need to select an appropriate contact resistance and an offset distance. You can check the offset distance is appropriate by turning on the Selection Updates Graphics button, which will highlight which elements are being included in the thermal links. This image here shows that the elements on the back of the human are going to be connected to the seat back. So it's like these elements shown in red are being connected via conduction to the elements in blue. For thermal links containing humans, it's important that you don't make the contact resistance extremely small. This will cause model instability or model divergence. The value shown here, 0.01, is a good recommended contact resistance to connect humans to seats or other cabin parts. When we import the human into the model, as a default, they will be nude. We want to make sure that when we complete the step of applying clothing, that we're choosing an ensemble that matches our scenario of interest. So for example, if you're running a heat up, the person should probably be dressed as if it's wintertime. If they're wearing like shorts and a tank top, the results might not really reflect what a real person in that specific scenario would be experiencing. Our engineering team recently developed this Human Thermal Clothing Manager tool, which allows you to select from an assortment of ASHRAE ensembles and automatically import those into the model. This tool is specifically beneficial for cabin modeling because you can select your ensemble based on whole body CLO. If you're unfamiliar, CLO is the standard clothing measurement to define the insulation of an ensemble. 0 CLO is a person fully nude, 1 CLO is like a business suit, and anything above 1 CLO is high insulation like winter gear. This tool lets you sort by the total insulation. So if you want a person with a summer outfit, you can make sure that the CLO is going to be below like 0.6. And if you want a winter outfit, you can make sure that you choose an ensemble that has a CLO of at least 0.9. If you're interested in using TAITherm to view the Berkeley sensation and comfort, You might know that whenever you change the ensemble, it's recommended that you obtain new set point temperatures. These set point temperatures allow the model to figure out if the human is cold or warm based on what their skin temperatures would be in a neutral environment. This HTCM tool will also generate new set points for you whenever you change the clothing. You can generate set points whenever you import a new ensemble, or even if you're not using the tool to import clothing, you can also just use this interface to generate set points if you didn't like the Berkeley set points utility running from the command line, which was the previous way to do it. To generate set points, just enable this Run Berkeley Set Points checkbox, and then you have to choose an activity type and an activity level. For cabin simulations, you should choose sedentary for the activity type, and 1.2 is what we recommend for the metabolic rate. You need that metabolic rate to get the set points, and you also need to set that metabolic rate within your TAITherm model. For driving, the activity level should definitely be a value somewhere between 1 and 1.5. It can vary the results a bit based on which value exactly you choose, so you do want to be intentional when setting this number. For a standard driving scenario, as a best practice, we do recommend using that 1.2 for the metabolic rate. That's kind of good for some kind of active driving. Convection modeling is going to be important on the interior of your cabin if you're doing like an HVAC heat up or an HVAC cool down simulation. There are a few different options available to you for convection modeling. All these options are valid. You just want to choose the one that gives you the result fidelity you need while balancing your runtime needs. Starting at the top of this table, the quickest option for setup and simulation runtime is going to be to just put a single bulk cabin air part in the middle of the fluid domain. This will calculate one air temperature based on interactions with all of the cabin surfaces. You might choose this method if you're really early in the design cycle and just want to quickly evaluate some options. It's not going to account for any air temperature gradients within the cabin, so the results will probably not be validation level, but they might be okay for like early comparisons. A slightly more accurate option is to have a network of air parts spaced throughout the cabin. This is going to give us some temperature gradients, and the runtimes will be comparable to option 1. You will likely have to use assumptions for the flow rate between these fluid parts, so this is still not a highly accurate method of modeling convection. Getting into more advanced modeling options, you could choose to use RapidFlow, which is our 3D flow solver that's going to run efficiently for heat transfer problems. It does create a full fluid domain mesh, so you will get accurate modeling of the air temperature gradients throughout the cabin, as well as accurate airflow based on your HVAC settings. This is also a single software solution, meaning you don't have to set up a second model or set up any coupling automation. The last option is to perform a CFD TAITherm coupled simulation. This method will also account for complex airflow patterns, but it does require that you set up a CFD model and some kind of coupling automation. This is a good option if you already have a coupling infrastructure set up, or if you have a CFD model already built that matches your TAITherm model. People typically use this method when they need highly accurate air temperatures, surface temperatures, or human results, maybe to validate against test data, or because they're at the end of their design process and want to be really rigorous in confirming their design choices before creating a physical vehicle. If you choose to use RapidFlow to model your interior convection, here are some suggestions for the configuration settings. These settings all get defined in the RapidFlow config text file. And these recommendations do vary based on what type of simulation you're running, so a soak, a cool down, or a heat up. In our testing of settings for cabin models, These ranges shown on the slide produce stable models with good results. Choosing different values within these ranges can help you to optimize for fidelity versus simulation runtime. For all RapidFlow models, the mesh for the fluid domain is automatically generated, and it's going to look something like the image on the right-hand side. Along with the internal airflow, we likely need to consider the wind over the exterior of our vehicle. The environment outside of the vehicle and the speed of the vehicle will have an effect on the internal cabin environment. There are a couple valid options for modeling external convection, which are listed here. The most common option is probably to set up a natural weather environment in the TAITherm model and use the wind convection algorithm. To set up a natural weather environment, you just need to compile weather data into the proper text file format. With all of the global weather data available for free on the internet, it's really simple to customize the weather in your model to match your specific scenario of interest. Also, you can define a vehicle speed in TAITherm, and the software will be automatically able to calculate a wind vector based on the wind direction, wind speed, as well as that vehicle direction and vehicle speed. Our next option is that you could choose to apply some constant H and T value based on external temperature and maybe some educated guess for that convection coefficient. This won't be super accurate, but it's maybe okay for like A to B model comparisons early in the design cycle. The most accurate option is using imported CFD results. Modeling external convection in a CFD tool requires a very high element count, so you should expect really long runtimes with this method. We mostly see people use this method if they really need to validate surface temperatures on the vehicle exterior. Otherwise, the runtimes don't really justify, or the results accuracy doesn't really justify those extremely long runtimes. Our last step in model setup is to consider what the starting temperatures of our human and our vehicle should be. The temperatures chosen at the start of a transient simulation are going to have a significant effect on the results throughout the simulation. Picture a hot summer day. If you enter a vehicle that's been parked out in the sun, it's going to start hotter and take longer to cool down than if you had parked that car in the shade. To get accurate results for our simulation of interest, we usually need to run some preconditioning model that simulates the environment of the vehicle and separately the environment of the human just before our simulation of interest. In this first option shown on the slide, we have a model that just contains our human. Maybe they're in an office or they're walking outside to get to their car. We would run this simulation of the human only so that we can later utilize those ending temperatures on all of the human parts. We also have a model of only our car, which is soaking outdoors in the environment. If there is solar included in this simulation, you'll want to start the simulation just before sunrise so the model can heat up appropriately. Run this car-only simulation until just before the simulation of interest begins. We can then use the transient restart feature in TAITherm to start all of the vehicle element temperatures as if it's a continuation from that vehicle soak. And we can use the human text files from our human precondition to start all of the human temperatures appropriately. The second option is valid if you have no solar loading. So if there is no solar, we can really just assume that all of the cabin temperatures are equal to whatever the environment air temperature is. So instead of running a vehicle precondition, you could just set all of the cabin parts to bypass steady state initialization. So they just start at exactly whatever the air temperature is at the start of our simulation. You do still want to run the human precondition, and we can now choose to set the human temperatures to transient restart from those human precondition models. Now that we've set up our models, here we're going to go through some tips for getting convergence when we go run these models. Models with complex boundary conditions or complex physics often require more conservative solver settings to achieve convergence. Cabin modeling often includes things like human physiology or phase change materials or fluid streams. All of these may require changing the solver settings from their default values, and also may require that you put some thought into the time step size. The best option for complex models is to use a time step size curve, which allows you to vary the time step size throughout the simulation automatically. The time step size might need to be small early on in the simulation, but using those tiny time steps later on is likely unnecessary and will just increase the runtime with no benefits. The curve shown here is a pretty standard example for cabin heat up or cool down with a human occupant. We can see that the time steps are really small at the beginning, like half a second or a second, and then it slowly gets larger over like the first minute of the simulation. If the boundary conditions change at any point during the simulation, to achieve convergence, you might also need to drop the time step size down at whatever point those conditions are changing. If you have a model with a lot of time-dependent curves, the easiest way to figure out what the time step size curve should look like is to make a little plot that just contains all of those time-based curves. And then we can just make a time step size curve where we drop down the time step anytime there's a change in our boundary conditions. That can really help us visualize and make sure that our model is going to converge well. Along with making sure to use an appropriate time step size, you may need to make the solver settings more conservative as well. If you're unfamiliar, you can find all of these settings in the Analyze Params Advanced dialog. The options in here will change the way that the solver runs, and they only need to be changed really to improve model convergence. These settings don't change anything else about the simulation or the results. They just kind of slightly change the calculations to make them, more likely to converge. I'm going to go through some recommendations on how these values should be changed from their default states. But if you want more information on what exactly all of these settings do, I would recommend looking through the user guide. It's recommended that you set the solution method to multigrid. That's kind of the recommendation for most models, and it's also true for these kind of cabin models. The multigrid solver should achieve more efficient convergence than the partial direct solver. The inner residual convergence criteria should be set to scaled. This improves the solver efficiency when using higher numbers of inner iterations. And you can leave the scaled value at 0.1. You may want to increase the maximum number of inner iterations to something around 30. The default is going to be 3, which is really usually too low for models containing human physiology. Decreasing the relaxation to 0.9 or 0.8 is helpful for model convergence, but if you decrease it lower than like 0.7, the model might become unstable again. The matrix update frequency should be probably increased to medium or high, and it's sometimes helpful to enable the multiple radiation sweeps option, and you can use the default value of 2. The settings shown here on the slide now are generally the best practice to ensure model stability for cabin simulations. So it can be a good idea to just go in and use these values automatically. But if you want to kind of play around with convergence versus model runtimes, you can adjust these slightly to see if you can get it to run faster or converge better. Even though we've hopefully set our model up for success by setting an appropriate time step size and defining the solution parameters, we still want to be checking the model convergence while the simulation is running to ensure that we can trust the simulation results. Make sure to use an appropriate value for this tolerance. The default value of 0.005 is usually good for most cabin simulations, so we're setting the tolerance here. While the simulation is running or after it's finished, you can view the convergence plot in this convergence tab. All of these spikes here that we see are going to indicate the start of a new time step. The line should basically go down until we reach that tolerance value, which we set to 0.005. Once we reach that, it's moving on to the next time step, so it might jump up again, and then it'll go down until that time step converges. So this is kind of generally what the convergence plot is going to look like. This would kind of indicate to us that the model is not running too many iterations for each time step and is converging well. You see here that this first time step takes like maybe 15 iterations to converge. It might take a few more iterations if the model includes more complex physics like moisture transport. But if you see that it's taking like 500 iterations for your model to converge, that might indicate that something is weird in the model setup, or that you should go change the advanced solution parameters that we just looked at on the last slide. If it's taking many iterations to converge, that's just increasing the model runtime and changing the multi-grid solver settings, or like changing your time step size curve might actually help the model to run faster. The standard convergence plot we just saw only shows you a model average value. So it can be a good idea to also check the convergence on specific parts. Usually want to choose parts that are kind of interest to your results. In the example on this slide, I set up some monitors before running the simulation so that I can check the results for each iteration on some specific parts of interest. This just lets me know that not only is the model converging as a whole when looking at just the average temperature change for every single element, but it specifically lets me trust the results on the parts that I'm most interested in. These lines are fairly smooth, which tells me that these are converging well. If they were like dramatically oscillating around, that would be a little suspicious, and I might want to check the boundary conditions on those parts or go back to the advanced parameters and make them more conservative. Now that we've run our simulation, we're going to take a look at some results that we might be interested in checking. Obviously, we want to look at our results of interest. If we were running a cabin simulation to evaluate human thermal comfort, we'd want to pull up some plots of the human comfort. But we should also maybe check other model results to give that results of interest a little bit more context. And maybe we want to also figure out how to format the data in a meaningful way. The majority of the human thermal results, like mean skin temperature, sweat rate, the thermal comfort information, those all get written to text files at the end of the simulation. It can be tedious to manually compile the data from those text files and organize the data in a way that is easy to comprehend. So our engineering team recently developed this thermal comfort analysis tool, which automatically compiles those human thermal results into a simple PowerPoint format for you. This tool is really helpful for general post-processing of the human thermal results. It can help you to visualize trends in the data and can also help you interpret what all of the metrics actually mean. We highly recommend using this tool as a best practice, both because it's definitely more efficient than manually compiling the data yourself, and because it also provides a good overall picture of what the human is experiencing. If you're interested in the overall comfort of the human, It's tempting to just look at that overall comfort value, but there is other human thermal data that you should probably check to get more insight into why the overall comfort is what it is. In the PowerPoint generated by running this tool, it will start by displaying some of the human thermal inputs. It'll show the ensemble CLO value, the activity level of the human during the simulation, and what state the human was in just prior to the start of the simulation. So were they cold, warm, or neutral, like the second before time 0? It's a good idea to check this information to make sure it all matches what you expected. It's a lot easier to catch model setup errors by directly checking the inputs versus seeing that the results look a bit unexpected and then trying to go and figure out why that might be. I'd also like to point out some results that TCAT will provide for you that could help you identify model setup problems or just understand the simulation better. When running human simulations, it's a good idea to check the mean skin temperature as well as the core temperature. The mean skin temperature trend should look expected for the simulation you're running. For example, in this plot shown here, the human entered a cold vehicle at the start, and then the HVAC was turned on in heating mode for the duration of the simulation. So this kind of trend here where they're getting cold when they enter the vehicle and then the HVAC kind of helps them to warm up again. This trend helps us confirm that the model was set up as desired. When we check the core temperature for cabin simulations, this should usually be a fairly flat line. The human body is meant to regulate the internal temperature at 98.6 degrees Fahrenheit or 37 degrees Celsius. So if this plot showed wild fluctuations or a dramatic increase or decrease, the human might be diverging or something about the simulation was set to like such an extreme value that the human is in danger. The tool will also plot equivalent homogeneous temperature, mean radiant temperature, and mean convective temperature. This plot can give us information about what is heating our human and what is cooling our human. The simulation that matches these results was a cabin warm-up using an HVAC system. And we can see that this MCT, so mean convective temperature, green line is above the EHT line. And this tells us that convection was the main mode of heating, which just kind of matches what we expected from the simulation. The tool will also show you the Berkeley overall sensation and comfort plotted on the same graph. It will color the uncomfortable sections red and the comfortable sections green, which just makes it really easy to see at what point exactly in this heat up duration the person started to feel comfortable. When using this tool, you generally just need to set the path to your TAITherm model that already contains human thermal results and a path to the TAITherm executable. But if you open the settings, there are some additional options available to build on the default functionality of the tool. You can have the tool generate plots of the Berkeley sensation, comfort, and skin temperatures for each individual body segment. You can add additional plots like sweating, shivering, or other comfort metrics like GTS or PMV. And you can also have all of the human thermal data saved to an Excel file instead of just having those text files where they are originally stored. And having this Excel file can just make it easier if you need to further examine the results. There are also some results that you may want to view within TAITherm. If you're modeling anything that has the potential to burn human skin, I would recommend checking the maximum temperature on the human parts as well as the average. If you're modeling like a heated seat, just using a constant heat rate, maybe you don't have a controller device set up to stop the heating, the surface of the seat might get very, very hot. In this plot on the left, we can see the pink is the average temperature of the human face and the green is the maximum temperature. And we can kind of see that the average temperature differs a little bit from the maximum. On a part that is interacting with like a local heating device, like a heated seat, this temperature difference could be fairly significant. If you only view the average temperature, you might be missing some elements that are getting close to the burning point, which is about 44 degrees Celsius. Another nice thing you can get out of TAITherm is animations of the thermal results. On the right-hand side, I have an animation of the temperatures over a 30-minute heat up. You can also make animations for human comfort, imported H&T values from CFD, radiation relations, any of those kind of main thermal results that you see in TAITherm. And if you're doing repetitive workflows, you may want to use the thermal report feature. This will save the definitions of all of your results exports. So if you always want to export a specific animation or a specific data from similar models, you can automate that workflow really easily using thermal reports. If you use RapidFlow for the convection modeling in the vehicle, you can view the cabin air temperature and fluid stream lines in pair view. This information on the airflow can provide more context into the results. If you're evaluating the HVAC system or human comfort, viewing this data might inform you on things like what is the optimal vent placement, or if the angle of the vents was effective for the human position. I'm going to now show a couple of cases on how you might examine the results to kind of figure out if something in the model wasn't quite set up right. And we can also look at how changing some of the inputs is going to change the results. In this first case, I ran a cabin heat up simulation with just one human occupant, so the driver. I used RapidFlow to model the cabin airflow, and I used a natural weather environment that was about negative 18 degrees Celsius during the simulation. To dress my human, I just chose to use the default clothing options within TAITherm. If you set up humans in TAITherm before, you may have noticed that there's just like a couple clothing options available as a default within the software. So I used these kind of basic shoes, a long sleeve shirt, and tweed pants. When I ran the simulation and looked at the results in that TCAT tool, I noticed that it was reporting that the overall CLO of the ensemble is only about 0.77. And that level of insulation is typically for like a spring or fall outfit. So it's kind of unlikely that a person would get into their car on this cold winter day in only this light shirt and light pants. If I use that human thermal clothing manager tool that we talked about, I can pick my ensemble based on an overall CLO or insulation that seems appropriate for the weather. So here I chose this ASHRAE ensemble number 16, and the CLO is now within that winter range at about 0.95. So this is probably a more appropriate outfit for the environment. My results are probably going to be a little bit more accurate to what a real person would experience. The clothing you choose will have an effect on the results. Here I have a comparison of the thermal comfort with that 0.77 CLO ensemble versus that 0.95 ensemble. The dark blue line here shows the higher CLO model overall sensation, which does get to neutral like at the end of this 30 minutes. Whereas this light blue line is my 0.77 CLO ensemble, which we see stays cold the entire time, so it doesn't really get close to being warm. Looking at a second case, I have my original clothing ensemble, and I've used an activity level of 1.0. So my clothing insulation is a little bit too light for my environment, and my metabolic rate is probably a little bit low for active driving. When I compare this to the same model but with the higher CLO ensemble and an activity level of 1.2, we can see that the results do vary significantly. The human is significantly colder, here this light blue line, throughout the entire duration compared to the dark blue line, which is my higher CLO, and higher activity level. Also looking at the comfort, we can see that with higher CLO and higher activity, our human reaches a comfortable state at about 10 minutes in, whereas with our other model, this overall comfort is the kind of brown line, and it doesn't report that they get comfortable at all. So this teaches us that it is important to choose realistic inputs for all the model aspects, because errors in the model setup can really compound in the final result. It's important to be intentional when picking our boundary conditions, but it's also important to investigate the final results that maybe don't look as expected. So if I got these cold results shown in the light blue and that kind of darker brown line, but I thought that the HVAC conditions that I chose should really result in my person getting warm within 30 minutes, it is worth probably investigating that to see if I set up my model in the proper way. The best way to do this is to run TCAT to check those slides on model inputs like CLO, activity level, initialization. That just helps you to confirm that you did set up the model as you had expected or desired. And also, even before that, we could just try to stick to our best practices for cabin model setup, and that will hopefully lead us to the best result. We're going to just wrap up with a couple additional suggestions to keep in mind as you create your own cabin simulations. Cabin simulations with human occupants may feel complex to set up and understand, but following our recommendations can help you to achieve quick and accurate results. If you want more information on cabin best practices, the best place to look is the thermoanalytics support site. Most of the information in this presentation is documented in our cabin thermal modeling best practices guide, which you can download directly off of the support site. If you don't have a support site account, I would highly recommend creating one. To make a new account, you just navigate to support.thermoanalytics.com. There's going to be a sign button in the upper right corner. You click that, and then you just select Create New Account. With your support account, you'll be able to download new or old versions of the software, search through FAQ articles compiled by our technical engineers, and you can also download the human thermal tools that I've mentioned during the presentation. The Clothing Manager tool and the Comfort Analysis tool are very helpful for efficiently setting up the model and understanding the results. So I would really recommend you download them if you have not already. If you're having difficulty with model setup or interpreting your results, feel free to submit a support request to our support engineers via the support site so that they can assist you. All right, that's all of our content for the webinar today. But let me know, Chris, if there was any questions that came through.
All right, yeah, thanks, Allison. Yes, we had a couple questions come through. Let's see here. So first one, are there templates or example projects available to help me get started on cabin simulations?
Yeah, so for examples, I would say that the best option is to go look through our past webinars that maybe have more specific case studies on like specific simulations. So for example, we have a webinar that's recorded on the support site that goes through how human positioning in the cabin can affect the thermal results, which might have some more information about heat up or cool down model setup and results. We also recently did one on RapidFlow, which goes into a little bit more detail about setting up the RapidFlow settings for soak models or cool down models. For templates, there is on the support site, if you use our automation tool, TAITherm, there is a TAITherm template that does automatic human model setup and a cabin run. That's a good place to start if you're interested in automation. We're also planning a webinar about that TAITherm template in the spring, I believe.
Thank you. What software licenses do I need to run TCAT or HTCM?
For those human thermal tools that I mentioned, you don't need any new software licensing. For both of those tools, it's possible to run them without consuming any licenses at all. If you have a support site account, you can just go download them for free. It's not associated with any new kind of licenses. When you run TCAT, if you don't have any licenses available for human thermal or TAITherm, you can actually generate all of those results that I showed without consuming any of the TAITherm or human thermal license features. If you one second. If you don't set the path to your executable, it will only read results from the text files instead of getting any data from the TAITherm model. So it actually won't consume any licenses at all. All this currently does when you set the application path is it grabs an image of the human geometry. So you can basically get like all of the results that TCAT provides without using any kind of licensing. With the human thermal tool, if you don't have a license available, you can send all of the clothing data to a CSV file to be imported later. That is a little more inconvenient, but it is possible to kind of use these tools without any licenses, and they don't require you purchase any new licenses.
All right. Well, thank you. Looks like that that will do it for questions. So that will complete today's webinar. We appreciate you all for attending. You will receive a follow-up email later today containing a link to watch the recording of today's webinar session. Again, thank you, Allison. Thank you all, and everyone have a nice day.
Thank you, everyone.